Hello, good morning, and welcome back. Last time we talked about our midterm exam. The average score is about maybe high, 94. Okay. Today we will continue our study and we will move on to chapter 11. That is special theory of relativity. Special theory of relativity. Okay. Before we start, why we want to study special theory of relativity over and over again? Remember, when you are undergraduate students, freshmen, you learn the special relativity for the first time, and then you study the electromagnetism at sophomore. You study special relativity again. Now we will study the same topic again. We study this special relativity because it's very useful. It can be applied almost all the fields. So you need to have a better understanding of the special theory of relativity. We give you 3 times to familiar with the material. So if you don't understand the material provided here, you can double check with Griffiths, with Benson, with other textbook, any textbook you want. The major difference here is we will use a beautiful mathematics to express the theory. Okay, so that's why we study special theory of relativity. First, Einstein's special theory of relativity is based on 2 postulates. One is laws of physics are invariant in form in all Lorentz frames. In all Lorentz frames. In special relativity, we often call the inertial frames a Lorentz frame. We call the Lorentz frame, the inertial frame, a Lorentz frame. Second postulate is the speed of light in vacuum has the same value c in all Lorentz frames. The speed of light in vacuum has the same value c in all Lorentz frames, independent of the motion of the source. The bases of the theory are covered in Appendix A. However, I just noticed I forgot uh, to provide Appendix A for you. Therefore, I will send Appendix A. I will upload the Appendix A in IRMS systems. Appendix A on an elementary level with an emphasis on the Lorentz transformations and relativistic momentum energy. Here we examine relativity in 4 dimensions, dimensional space x and t, 4-dimensional space x and t, which provides the frameworks for us to examine the laws of mechanics and electromagnetism. The contents of the lecture notes now depart slightly from chapter 11 of Jackson. Yes, it departs slightly from chapter 11 of Jackson. Most of the material presented here are consistent with Griffiths. Therefore, let me show you the Griffiths 2 postulate. Actually, different textbooks use different postulate. Here we have 2 postulates. One is the law of physics are invariant in form in all Lorentz frames, and the speed of light in vacuum has the same value c in all Lorentz frames. However, Griffiths description is slightly different. His two postulates. One is the principle of relativity. All physics laws have the same form in all Lorentz frames. The principle of relativity. Laws of physics are invariant in form in all Lorentz frames. Which one is more convenient? Which one is more uh, much easier to remember? I think it's uh, maybe is Griffiths. Second, the universal speed of light. The speed of light in free space, and in previous one we say vacuum. That's equivalent. Vacuum means nothing. So it's free space. It's the same in all inertial frames. Inertial frame is Lorentz frames, equivalent. It does not depend on the motion of the source or the observer. So if we have an incoming light, we measure the speed. If uh, if two trains, one comes from right to the left, the other comes from left to the right, and we have a ball from here drop to release to here, and the physics laws has the same form in this frame and in this frame, or in the rest frame. The physical laws are the same. And if we have a if, if we have a flashlight emitted a light from here to here, and different inertial frame will see the same speed of light. C. That is, the speed of light in free space is the same in all inertial frames, in all Lorentz frames. Okay, these two postulate is Griffith's postulate. Okay, so we have two postulates. Both postulates are restricted to inertial frames, Lorentz frames. That's why the theory is special. So we say it's a special theory of relativity. The principle of relativity extends to the concept of covariance from mechanics to all physical laws. Not just mechanics, but to all physics law. The constancy of the speed of light is difficult to accept at first. All the experimental consequences have confirmed this correctness. So these two postulates, up to today, yeah, correct. Okay, so move on. This chapter we divided into three sections. Section 1, we will define and we will give you the definition and operation rules of tensors of different ranks in a four-dimensional space. Okay, in a four-dimensional space. Four-dimensional, including three position space and one time space. Yeah, a four-dimensional space. I will tell you the definition of the tensors and operation rules of tensors. Lorentz transformation. I think the most important transformation is Lorentz transformation. We consider two Lorentz frame, two inertial frame. One is K and K prime. Frame K prime move along the common x-axis. So x-axis is the common x-axis with constant velocity v. relative to frame K, just like this one. We have K prime move relative to the old frame, K frame, with a relative speed V, okay, in a common X frame. We have X, we have Y, and we have Z. You might wondering, in a previous case, in a wave, we prefer the common axis is the Z axis. But here, we use the common axis is a S axis. Can we change the common axis to Y axis? Yes, we can do that. We can do that. But here, I will show you why we prefer X axis. Very soon. We assume that at time equals 0, that is t equals 0, t prime equals 0. The coordinate axis of frames k and k prime overlap. That is, at t and t prime equals 0, the origin overlap. Okay? Postulate 2 leads to the following Lorentz transformations for space and time coordinates. Okay, so you can study the appendix A by yourself, and you will find the Lorentz transformation. Yeah, give you agree with the postulate 2. I will give you more information about how to derive the Lorentz transformation. Recently, some professors from Russia, he told me he has some new derivations, and I will show you. I will give you some reference. Okay, where the relative motion is assumed to be along the x-axis. Okay, so that's the Lorentz transformation. We have two coordinates, 0, 1, 2, 3. This stands for t, x, y, z. Okay, so the common axis is s-axis, t, x, y, z. Okay, so you have two expressions. S0 prime, K prime system, K prime frame can be expressed as X as K frame. On the other hand, K frame can be expressed as K prime. The major difference is the speed is different. So go to here. If we consider this is a rest, so the coordinate here, this one, this one, this one can be expressed as this one, this one, this one, and this one. On the other hand, if we consider this one as rest frame, this one will be moved in the opposite directions, minus v to here. Okay, that's the relative motion. So we have two expressions. The major difference is here. One is positive v, the other is negative v. This is positive, this is negative. Sorry, we have minus beta here. Beta is v over c, and gamma is 1 minus beta squared. It must be greater than 1. This one is from 0 to 1. This is the absolute value, so the speed, not the velocity. So speed is, the minimum speed is 0. The highest speed is c. The limiting speed is c, universal speed of light. So gamma will be, the minimum value will be 1, and the maximum value will be infinity. That's 11.17, the Lorentz factor. Okay, two expression. Let me show you the three-dimensional expression. That's for three-dimensional, not for four-dimensional. In many books, the relative speed between two frames is denoted by v. Okay? The particle velocity in a given frame is denoted by u. Particle velocity in a given frame, in this case, in prime frame, is given by u. Okay? So the eventually these two definitions for the same notation. One, as gamma, Lorentz frame for the transformation of Jackson's two coordinates. Second, the Lorentz factors of a particle in a given frames. In a prime frame, K prime, we should use U prime. However, in here, if we describe the motion of particle P, we should use another notation as U. That's the relative motion of the coordinates, the frame, and relative motion of the particle. We use two expressions. One is V, the other is U. Okay, that's for three-dimensional, and for four-dimensional, the same. Okay, the space-time continuum is defined in terms of four-dimensional space with coordinate x0, x1, x2, x3. Okay. For special relativity, x superscript or underscript will be different. Slightly, I will show you. But right now, we just denoted it as superscript x0, x1, x2, x3. Suppose that there is a well-defined transformation that yields new coordinates s1, s0 prime, s1 prime, s2 prime, x3 prime. According to the rule, the prime system will be related to unprimed frame, and alpha will be runs from 0, 1, 2, 3. So a little change in x alpha prime, we can use the chain rule. The change in x0, the change in x1, change in x2, change in x3. Since alpha runs from 0, 1, 2, 3, so we can write into a four equation. Each one has four components. So we can express the x prime 0, 1, 2, 3 as the matrix times another the x unprime system. So we have some coefficient here. That's a transformation matrix. Transformation matrix is shown here. X prime, 0 prime, x0, x1 prime, x1. Diagonal is different, the same number, the same superscript, but one is prime, the other is unprime. So we can define a notation here. Lambda. This looks like the velocity u, but actually is mu. Okay, They change the color. This one. M, U, mu. And what happened here? Okay. That's mu. That's new. Okay. Looks like the velocity u, like the velocity v, but actually it's pronounced as mu and nu. Okay. So it's different. Okay. So we use capital lambda, lambda, mu, superscript, subscript, superscript, superscript, sub, subscript. Okay, so lambda, mu, nu is just a definition like this one. X prime mu, partial x nu. Okay, one up, the other is also up, but remember it's in the numerator, is in the denominator. So we change numerator into here, denominator into here. One up, the other down. Superscript, subscript. Okay, so this is the notation transformation. For the moment, the transformation law is not specified. We don't know what is this looks like. Okay, a Lorentz transformation matrix. We have four coordinates: x0, x1, x2, x3. And we know x1, 2, 3 is the space coordinates. So s0 is impossible to be time, must be in the same dimension. But time, x, y, z, and t. Therefore, we add a speed c here. We add a speed c here. C times t, velocity times time. Therefore, it becomes displacement. Okay? And beta is defined as mu over c. C is the speed of light. Mu is the speed of relative motion of the frames. Two Lorentz frames, two inertial frames. So we got this one. S prime 0, S0 prime related to this one. S1 prime related to these two. And others do not change. Okay, that's the Lorentz transformations. Be more specific. So in O, we can express the coordinates to be this form. And gamma will be here from 1 to infinity. Beta will be from 0 to 1, the maximum value. Okay, so prime is shown here, and Lorentz transformation, the matrix. Go back. This matrix should be independent of coordinates. it's just a constant, depends on velocity only, depends on the relative motion. So this is a just a constant, depends on velocity, proportional constant. Okay, and here we use 0, 1, 2, 3, 0, 0, 1, 1, 2, 2, 3, 3. Okay, we take the derivative, dx prime, dx prime. Let look very simple, just here and here. Okay, and lambda is mu. So the problem is this is velocity v. This is the index nu. Quite similar. It's very difficult to tell the difference. Very difficult. Just keep this in mind. Let's not velocity, just an index. Let's not a velocity, just an index. The same. Okay. This is Lorentz transformation matrix. Lorentz transformation matrix. Okay, looks good. Move on to the next slide. Now let's explain why sometimes is superscript, sometimes is subscript. What's the major difference? Actually, we have a control covariant and control variant vectors. Any set of 4 quantities, A alpha, alpha runs from 0, 1, 2, 3, you can denote as a vector. Okay, A0, A1, A2, A3. So this is a 4 quantities which transform in the same ways, in the same way as X alpha. That is A alpha prime equals summation beta lambda alpha beta beta. Beta runs for 0, 1, 2, 3. Sum over that, sum over all the common terms. Let's call a 4 vector. That is any set of quantity, which transform in the same way as this one. It's called a 4 vector. That is a 4 vector always transform in this form. A 4 vector always transform in this form. And beta runs from 0, 1, 2, 3. That's Einstein summation convention. It simplifies the notation a lot. In the old time, it's quite important. But now we have computer. It's not necessarily so powerful, so it's up to you. For tensors of rank 1, we call tensors of rank 1. Obviously, later on, we have a tensor of rank 2, tensors of rank 3. Tensors of rank 1 we call vectors. Two kinds must be distinguished. One is covariant vectors, control variant vectors, A prime alpha. So transformation is exactly the same. The other is covariant vector, beta alpha prime, subscript, up, down, 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 up, down. So you have two expression. One expression is sum from one two expression. A prime alpha is sum here and here, and control variant is sum here and here. So that's different in notation. Okay, let me show you what is the difference between x alpha and x superscript alpha and x subscript alpha. To understand these two notation, we need to know the metric tensor, or the norm tensor, metric tensor. Just consider, if you want to measure the distance of a line, let me show you. From this point to this point, the distance of a line x 1, y 1. Here, x 2, y 2. How to calculate the separation? x1 minus x2 absolute value square plus y1 minus y2 absolute value square, and take the square root. That's the separation. If we have three z1, three-dimensional, z2, then how to calculate the separation of 2 points? The change in x, the change in y, the change in z square, in y square, in x square, and take the absolute value. Okay, how about 4 dimension? In a special theory of relativity, Lorentz transformation of the 4-dimensional coordinate follows from the invariant of two events. Okay, the invariance of two events give us this information. The x squared equals the x0 square minus the x1 square minus the x2 square minus the 3x square. Let's get an event occur in the space in time, and by two observer. One is two observer. Then two observer in a space, two observer in a different space time. Then we'll see the same phenomena. Maybe I should not say that. Just give you an idea. If we have in this coordinate, and I just do some gesture, I clap my hand here. I clap my hand here, and then clap my hand at another time here. So T1, X1, Y1, Z1, the first event. Second event, T2, X2, Y2, Z2. And we know one thing. The separation between these two events. How to calculate the separation of these two events? We can do that. The x2 equals the x0 square. X0, that's c times t. C times t minus the change in x the change in y square, the change in z square. Okay, two expression. We can write another notation, x alpha, x beta, but this time we use a notation called metric tensor. Metric tensors. Metric tensors allow us to estimate the separation of two events. It's called a metric tensor. What's the difference? No cross term, no cross terms. Therefore, G alpha beta equals G beta alpha. And in flat spacetime, inertial frame, special relativity, we have a very simple G metric tensor. 1 minus 1 minus 1 minus 1. So the covariant metric tensor G alpha beta is defined as the normalized cofactor of G. For flat space, it is the same. G alpha beta equals G alpha beta. For flat spacetime, flat means no curvature. However, if the space is curved, then how to calculate this one? Just imagine we have something like, maybe I should draw a figure like this. A figure like this one. That's a curved space. Not good. In a curved space, the tensor will be different. But now let's focus on spatial relativity. So we have a lucky simplified symbol. Okay, that's good news. So what is the G? The contraction of the covariant and contravariant metric tensors give us a simple notation. That is the connected delta in 4 dimensions. G alpha gamma, G gamma beta. So we sum over gamma. The result will be delta beta alpha. That is Einstein's summation notations. Sum over gamma. Gamma runs from 0, 1, 2, 3. And G beta gamma is the same as this one, no difference. Alpha gamma, gamma alpha, the same. Okay, so this is a connected delta. That is beta alpha will be 0 unless alpha equals beta. Then it will be y. So connected delta will be 1 or 0. 1 or 0. Therefore, if we want to change from contravariant to a covariant, just use G metric tensor or norm tensor, sum over beta, and eventually you got a subscript. If you want to raise this one from a subscript to superscript, just times G alpha beta and sum over beta. So with the metric tensor, a covariant vectors and a contravariance can be expressed as this form. If we have a vector, this is obviously a covariant, and this is a contravariant. So CT will be the same. Not necessarily be a CT, but if we have a Lorentz vector 4 vector of the first kind, first rank 1. For tensors of rank 1, we have these expressions. Okay, very convenient. And later on, I will show you the section 2. We will give you a different, for example, 4 position, 4 momentum, and other 4 vectors, 4 velocity, yes, and 4 potential. I will show you a lot of 4 vectors. They will transform in this form. Okay, I will give you 2 examples. One is the length contractions. Let me show you. The transformations between 2 inertial frame, x and x prime, are here. We don't have to worry about y and z because y and z no change at all. We have x and prime rest. Prime is moving at a velocity v relative to the unprimed system. If we measure at a coordinate t equals 0, then we got this one. Delta x equals delta x prime divided by gamma v. But when you measure at another coordinate, if we want to measure the length, we need to measure at the same time, at the same coordinates. So if we have a ruler, we have a moving train. This moving train, if you want to measure its length, you should measure at the same time, in the same coordinates. And then you will find that their velocity, their length will be different. Okay? However, in the opposite, that's the relative motion. Physics principle of relativity. Physics law will be in the same form. I'm prime, I'm prime. Okay? Explain why the length relation depends on simultaneity, 同时性. Okay, so let me show you. First, if we measure at the unprimed system, so delta t equals 0. Obviously, it becomes gamma v delta x. Okay, so we can change to here. We just assume this one is delta t equals 0. Delta x prime gamma mu. This is a constant, a proportional constant. And delta x. So we can write into here. Which one is at rest? Delta s prime is the proper length because it's at rest. On the other hand, if we measure at a different condition, delta t prime equals 0, then delta t prime equals 0, then delta t prime equals 0. Therefore, they are correlated. Delta t equals this one. Therefore, delta x here, delta t, delta x prime equals delta x minus v delta t, and delta t is related to here. Let's substitute into here. So eventually we got a simple relations. Gamma gamma v equals delta x minus v squared over c squared. And here is equals gamma v squared. 1 over gamma v squared. So eventually can be written into this form. So in two different systems, the proper length is different. Two events that are simultaneous in one inertial frame. Two events that are simultaneous in one inertial frame are not simultaneous in another. That is, if we have two frames, we want to measure the length, we need to measure at the same time. That's simultaneity. If we want to measure, for example, if I want to measure the length of a book, we should measure at the same time, not different time. If we want to measure the book and the book is moving, that's not good at all. However, if we measure the book and book is fixed, do not move in our frame, then we can, delta t will be the same. All we need to do is measure, okay? So if we want to measure this frame, we have another, that's proper length. And on the other hand, if we want to measure, and so if we have a moving book, one frame is fixed, the other is moving, just like this one. And we have a moving, we have a ruler here, okay? Ruler, we can measure from here. Ruler is, if this one, then this one will be a ruler here. Okay, if we have a 1 meter ruler, and from this one's viewpoint, the 1 meter ruler will become shortened because it's in a moving frame. On the other hand, if we have a 1 meter ruler and it's fixed in K frame and looks like it moves, its relative motion is here. Therefore, from this viewpoint, the ruler will be shortened. It depends on the observer. And because of simultaneity, we will obtain that two events that are simultaneous in one inertial frame are not simultaneous in another. Okay? So it will be much easier to understand if I give you some gestures. Okay, let me give you another example. Let's velocity addition rules. Velocity addition rule tells us that the transformations between two inertial frames, S and S prime, are here. Okay? Suppose a particle move at a distance dx in x in a time dt. Its velocity is defined as u. U is defined as dx over dt. Show that the velocity measured at s prime, what is the velocity looks like? Okay, if we measure at the x prime, then gamma mu the same dx minus v dt, and the t prime will become this one, and u will become the ratio between the x prime, u prime becomes the ratio between the x prime over the t prime, and the x prime is here, is shown here. That's the x prime. dt prime is also shown here. What's next? Let's divide by dt. And so this one will becomes u. And this one is v minus 1 minus uv over c squared. Therefore, the velocity measured at x in another in primed inertial frame, Lorentz frame, will be different than this one. Okay. If u and mu are very, very small, for example, a few meters per second, a few centimeters per second, then these terms will be very small. So u prime will be equals to u minus v, the simplest case, Descartes coordinates. But here, we use Lorentz transformation. In a special case, let's consider if u is very close to the speed of light, what will happen? And v is equals minus c. We got u prime still equals to c. That's one is moving forward and observer is moving backward. The speed of light in vacuum has the same value c in all Lorentz frames. Universal speed of light, independent of the motion of the source. We can verify this argument easily from the knowledge of velocity addition rule. So it's impossible to exceed the speed of light from this viewpoint. Okay, maybe I should stop here. Next time, I will give you four-dimensional space quantity and operation rules in more detail. We will write it again, and we will show something looks like inner product. That's three-dimensional. And later, we will give you something looks like four-dimensional and give you more example. Energy and momentum becomes a four momentum. And Lorentz scalar, Lorentz invariant, the idea of these two. And we will define operator, how to express the operator. Before we stop, I would like to show you many textbooks has different expression for Lorentz transformation matrix. For example, sometimes they use XYZ and CT, X1, X2, X3, and X4. In that case, the CT is is right after Z. But in this textbook, we use X0, S1, S2, X3. And for example, in Marian, he used similar, but he used imaginary. It do not use minus gamma, he used I gamma. And time, he used ICT. Okay. In order to not confuse you, I don't want to spend too much time. Let's focus. Let's use the notation here. And the notation here is consistent with Griffiths. So you don't confuse yourself. Much easier to understand. So next time we will start from page 12. Okay? I will stop here. See you next time.